You should be seeing my slides right now. Is that correct?
Yes, this looks great. We can see your presentation.
Thank you. All right. So like Stacy said, I'm in charge of presenting an area. So I'm presenting the Firearms and Toolmark Analysis area. And the basic outline for my talk is that I'll go over the general research question, present our results from CSAFE 1.0, and then present our plans for CSAFE 2.0. So for firearms and toolmarks examination, the currently established comparison standard is given by the AFD theory of identification. And very, very roughly summarized, that means that firearms examiners first examine class characteristics of a pair of evidence. And then if those class characteristics do not disagree, there's going to be a microscopic analysis, usually on a comparison microscope, to assess detailed features for similarity or dissimilarity. And then there's a range of conclusions that can be drawn, ranging from making an identification, so saying that these two pieces of evidence come from the same source, were made by the same tool, to elimination or exclusion, that these two pieces of evidence do not come from the same tool and come from different tools. So there's been, in the past, starting in 2009 and then repeated in 2016, some criticism from the scientific community in terms of the scientific foundation of the identification process, in particular about problems with establishing error rates in this identification process. An additional problem was shown to come up in proficiency tests in Europe, where subclass characteristics are concerned. So subclass characteristics, so characteristics that come from using the same tool to make a barrel or to make a screwdriver, that are not unique to this particular tool, but shared across all of these screwdrivers, all of these barrels that were made by the same tool. So those kind of subclass characteristics are a key risk factor for making false identifications. So in terms of CSAFE 1.0, our accomplishments. So what did we accomplish? And there's a lot that I would like to talk about. I only have a couple of minutes, so I just want to point out the highlights. So we've come up with 2 automated matching algorithms, one for bullets, the other one for cartridge cases. And we've made all of these matching algorithms openly accessible in software that is packaged and available for everybody to use. So open source, publicly available algorithms. There's 3 packages listed here: cartridge 3D, X3P tools, bullet extractor. There's a whole range of other supporting packages, and you can find all of them on our websites, and they're publicly available, free to use. The other big piece of the firearms project for CSAFE 1.0 is we have made a lot of data publicly available. We've managed to scan about 25,000 land engraved areas in our high resolution lab here at Iowa State. We've also got scans for about 2,000 cartridge cases. Those are also publicly available through the NIST Ballistics Toolmark research database. And most of them are uploaded by now. So when I'm saying 25,000 scans, I hope this looks like a large number. This is also a huge collaborative effort, and it would not have been possible all by ourselves. This is only possible because when we asked the community to help us with getting materials to scan, the communities stepped up, and it's really overwhelming, and it's really exciting to have all of these community collaborations in place. And I hope that for CSAFE 2.0, we can again make use of and leverage these collaborations and build new collaborations. Like Alicia said, building these bridges is extremely exciting. And when we had our pre-meeting for discussing the slides yesterday, we didn't have a room. We had only a virtual room, but there was palpable excitement in the room about the prospect of being able to continue with this research and to go down further routes. So where do we go from here? What we want to do with CSAFE 2.0. So first of all, there's not just ISU involved, ISU and CMU, I should say, but we've got 2 more leads coming in for Firearms and Toolmarks analysis. Those are Professor Keith Morris from West Virginia University, and Professor Maria Coelha from UPenn. So besides the research that we have done in matching bullets and cartridge cases, we also want to expand on looking at subclass characterization, analysis of firearms, and then also go into a Toolmark analysis. So let me quickly go through each one of these lines of research, and then I'll come back and summarize where we could immediately need help from the community. I'm sure that later on we will come back to you and ask for even more. So statistical algorithmic approaches to matching bullets and cartridge cases. So we want to build on our algorithms. We do have an algorithm in place that's essentially dealing very well, that has shown to deal very well with traditionally rifled firearms. We want to expand those algorithms to non-traditional rifling, build a bigger feature base that's also taking into account some image detection. We also want to investigate factors that affect matching performance for the algorithm that is mostly due to factors that actually affect how well stria in bullets are expressed, or how well a cartridge case, how well how well a firing pin, for example, a breech face shows on a cartridge case. So we want to look into combinations of firearms and ammunition. And then we also want to qualitatively assess the quality of scan. So if you have a look at those 2 scans that are in the top right of the image, these are 2 scans that are made of the same land. It's the same land engraved area, it's the same bullet, just taken at different points in time, using here actually a different lighting set. And you can see that the bottom scan is visibly of a much better quality than the top scan. There's a couple of things that we can do quickly, like looking for the number of missing values in the scan. But the assessment of the quality of a scan goes much further than that. So that's one thing that we want to look at more deeply with CSAFE 2.0, and then expand on an assessment in the matching algorithm to also consider the quality of these scans. We also want to work on getting the matching algorithms into the labs. So work with firearms examiners and crime labs to get our the matching algorithm into the lab. So in terms of the impact that we hope to make is provide quantitative assessments of evidence that will help examiners during testimony in the legal process. I think what we've shown empirically is that firearms and toolmark evaluation has an objective algorithm behind. There's an objective algorithm behind the assessment. And what we also want to work on more is to develop more confidence and more trust in the community on these algorithmic results. And that also means that we have to build up not just blind faith, but also some critical assessment of assessing where the algorithm works well and what the limitations of these algorithms are. That's it for the line 1 of investigation. The line 2 is led by Professor Keith Morris and consists of an analysis of subclass characteristics in firearms. So the plans are to collect data in the first place, to collect a reference collection of contender G2 breach faces, to expand on reference collections from different forensic laboratories, and then go into a characterization of the manufacturing process of breach faces. So characterize situations in which subclass characteristics might occur, and then work with firearms examiners to identify these areas. So work with firearms examiners and then go into an algorithmic evaluation of these situations. So there's various different automated algorithms available. One of them has been proposed by NIST, the congruent matching cells algorithm. And the idea is to use this algorithm in situations with and without subclass characteristics to see how the algorithm is doing in these situations. There's also the idea of coming up with a markup, graphical user interface, so a GUI, to help with marking scans, marking virtual renderings of scans for subclass characteristics. So we can then use these test fires to come up with proficiency tests. So we can both use digital scans and also use double casting to create replicates of materials collected. So like I said, for proficiency tests and accuracy testing in terms of identifying subclass characteristics for firearms examiners, and then also the same holds true for algorithms. Come up with an assessment of the performance and accuracy of these automatic matching routines. That's it for the second line of investigation, and I'm sure that Keith will answer any more detailed questions. The third line of investigation is regards the Toolmark analysis. So the idea is to come up with a database of tool marks. So that includes images in 2D and then also 3D images. And the idea is to build a database that covers a lot of different aspects of Toolmark, of what can happen with tool marks. So with firearms, we know that the brand of firearm matters a lot. The type of ammunition used matters a lot. So for firearms examination, we would have those little replicates, like you can see on the right-hand side. We've got the breech face images for a Ruger, a Sig Sauer, a Smith & Wesson. We've got several firearms. So firearms are these, we've got 4 firearms for each of the brands. And then we've got various different types of ammunition. So you can see here, we've got 3 types of ammunition. And that makes up 9 images of cartridge cases for each combination of firearm brand, the actual firearm, and then different types of ammunition. With tool marks, we have similar things, degrees of freedom that affect how a tool mark made by a particular tool looks like. So for screwdrivers, the way that the screwdriver was made is important. The brand of screwdrivers, the angle under which a mark was made, the surface material matters, whether the tool was used to make a scratch, a striation mark, or whether the tool was made for an imprint, so it just hit something. So all of these different degrees of freedom, all of these parameters can be captured and starting with a database, we can then come up with an algorithm to determine whether 2 tool marks were made by the same source. So that's the next step. And then once an algorithm exists, the next step would be to validate this algorithm by testing on materials where we know the source and see whether the algorithm is able to detect same source or different source. It's important to start simple. So even though there's all these different moving parts, it's important to start with just a simple tool, so a screwdriver in this case, and vary some of those degrees of freedom, collect data, and then in a next step go out and collect some more data to expand on the method. So this means that we will have a research base, or we're building a research base for further research and expand the capacity with which Toolmark analysis can be done in labs at the federal, state, or local level. So where do you come in? We need your help. So to all of the forensic examiners out there, what would be extremely helpful for us is to know about all of these lab rules. Labs have different operating procedures. It would be good for us to know how tool marks are assessed in your lab. So if you could send us standard operating procedures for your lab, that would be extremely helpful, so that we don't try to do something that's completely opposite to what you're actually doing in the lab. We're also still on the lookout for any kind of test fires. So anytime that you can spare, going through your reference collections, think of us, and if you have time, put in 4 test fires and send those to us. The address is available from our website. I can also email any one of us and we will come back to you. If you have any kind of studies, so past studies or ongoing studies, think of us. We would be excited to get your material scanned and expand on the available database at NIST. To all of the forensic analysts, there's a lot of proprietary algorithms that we don't have access to, but what we do have access to is publicly available data. So if you could run the proprietary algorithm on publicly available data and make the results publicly available or available to us to host it someplace, that would be also extremely helpful. Thank you. I'd be happy to take questions.
Thank you, Heike. We have Heike and the other 2 project leads in this area promoted to panelists. So if you want to go ahead and raise your hand, we can address questions to any of them. Looks like we have 1 person with their hand raised.
Hello, can you hear me?
We
Yes.
can hear you, Ted. Hi.
Oh, hi, Heike. I have 2 questions. First, one thing I may have missed in the introduction, I was particularly interested in 2 or 3 of your slides. So will they be, this is the first question, will they be available right after the session today?
Yes, they will be.
Accessible by the rest of us?
Yes.
Okay, very good, great. And the second one was, I was curious as to why Keith was using the contender G2 model as his first example for subclass investigation.
Hi, Ted. This is Keith Morris speaking.
Hi.
What we're intending to do is to actually manufacture some breach faces, and the contender has a removable breach face, so that allows for the interchange of breach faces. So it's not about the firearm specifically; it's about its ability to allow for changing of breach faces.
Great, thank you.
Heike, there is a question in the Q&A from Roy Maxian, if you want to go ahead and take a look at that question.
Oh, yes. Okay. Yes. So Roy is asking what our ability is to reproduce a cartridge analysis, starting with taking a new photograph and ending with the same outcome. That is a very good question. It's actually not me who should answer this question, but our fresh PhD, Dr. Keegan Rice. This is 1 chapter of her thesis that she has been investigating. Variability in results and also reproducibility, computational reproducibility of results. As statisticians, we often take computational reproducibility for granted, and that's not quite what we should be doing. What Dr. Rice has done is to come up with a tool. So yet 1 more of these are packages that are out on our website. So come up with a tool that helps us to assess whether we will get the same results in half a year's time, even if some of the code base has changed. Not just computational reproducibility, yes. If we have the same picture, so if we have the exact same data, we will get the same results given an unchanged code base. but it depends on, there's different, if we have different people taking different pictures of the same material, there are some sources of variability coming in through this identification process, because we have the additional scanning process in this identification picture, in this identification process.
Heike, there's another question in the Q&A.
Okay.
Are you aware that the FBI laboratory has already done research on test fires using different ammunitions?
This is from Eric Smith.
Yes. I am partly aware. I'm not aware of anything that's publicly available yet. But I'd be happy to see those results and see those scans.
Thank you. And there are a few collaborator suggestions in the chat window. We will save the chat window and make sure that the Firearms and Toolmarks group gets the contact information that's provided there. So thank you for those. We have 1 more minute if there are any final questions for this group before we move on to our footwear research group.
Ted raised his hand earlier. He is able to speak should he want to.
Oh, okay, thank you. I guess it's a detailed question. Heike, when you showed the 2 images of the same impression, bullet impression, and they look quite different, were they taken with the same instrument? Do you know the conditions were different under which they were taken?
I know, that's a great question, Ted. I know that the scans were taken by the same instrument. The only difference is the staging. So the scans were staged on different, the bullets were staged on different days, and the lighting protocol is different. So this is actually an example of something that went wrong in the last 3 years, or went wrong early on. So we had problems with a certain set of bullets. This is a particular bullet from a Ruger that has very deep stria. And the stria are so deep that our light did not go all the way, or our usual standard lighting setting didn't go all the way down into the crevices of the striations. So we did change the lighting protocol, but I'm keeping this example as an example of what we do not want to see in our scans. Yeah, good question.
Thank you.
Okay, thank you, Heike. We'll now have Charles begin his presentation on footwear. This is Dr. Charles Falks from the University of California, Irvine.